All right. All right, so I was getting close to finishing up the application part of the exam, and then I had a student interrupt me. I was getting close to finishing. We'll have it back on Monday. I'll have it back on Monday. Did grade the closed book portion of the exam. I sent you an announcement with that. Some of you did okay. Some of you did well. Others, not so much. And I went back and looked at averages for this part of the exam from years past, and yeah, this year's lower. Leave it at that. So the intention is to have like essentially a retake of that closed book portion. That retake will be online, but you would have to take it here. So what we do, since we'll get the exams back on Monday, you'll get the exam, you've got the week to kind of review. And this will be including the definitions and stuff. That front page should just be pretty easy. Just memorize your definitions. All right? We'll have that a retake of that in lab that next week. So if we look at dates, I believe that's November 1st. We'll do our regular lecture, probably cut that lecture portion short, so then we'll have the online version. And there is a time limit to that. All right? What I plan to do then is to take the higher of the two grades. So if you're happy with your grade for part 1 of that exam, and you don't want to take it, you don't have to. You don't have to take it. If you didn't like your grade and want to take it, yeah, you can. Or if you've got a grade and say, yeah, I think I might do better, there's no penalty if you do worse. You keep that higher portion. I think part 1 was out of 50 points, maybe. So, you know, the quiz or this retake might be out of 50 points. It may be out of less, maybe out of more. What we'll do is we'll scale it to the 50 points, so it's an even replacement if we have a replacement. But it'll cover the material that we did have. So it's probabilities that, you know, the definitions that we had all on that first page. So the probabilities, we had the homework, we have, you have the exam now, and I think I won't post the key to that part of the exam. So that way it kind of makes you have to get in and try to do it yourself and learn and work it out yourself. All right, you'll need a calculator, and we'll have the normal table and the t-tables again. I'll just bring them down so we've got them covered. Some of it will be multiple choice type questions. Others it will be like fill in the blanks. And for all of the answers, you can type your answer, and I'll tell you to round appropriately.
Or we need like a scratch piece of paper, that way we can work stuff out.
Yeah, you can have a scratch piece of paper. Yeah, we've got loads of scratch paper down here. All the stuff that gets printed. All right. So far, the part 2 of the exams, not looking terrible. There were some common mistakes that I've been seeing repeatedly, but nothing that's like overly bad. So yeah, part 2 is going to improve some grades, but yeah, I think the material in the sections is important enough to where if we do this retake of that part 1 of the exam, gives you a chance to like reinforce that material because you'll see it again on the final. All right. So I'll remind you next week when we pass that back.
Is homecoming week and registration and midterms usually all on the same week? Because that would That was not a good decision.
Well, homecoming. Our exam was on Monday. Well, I guess homecoming was that weekend, right? Yeah, if you still weren't feeling good on Monday after homecoming weekend, take that as a sign. Learn that from experience. All right, so this is here. So confidence intervals, right? We talked about 95% confidence intervals, and our intervals were, here it is. Here's our equation, right? And the assumption was that we're normally distributed. And if we're normally distributed, that allows us to use our t-distribution to approximate the mean. All right, this is why we'll do like a 2-sample t-test, why we use a t-distribution for that. But a lot of times we're working with data that are not normally distributed. Either their underlying distribution is some other distribution, or it's just your sample produced skewed data. So how do we come up with, let's see here, yep, how do we come up with a confidence interval that doesn't make that normality assumption? Well, the way we can do it is to do bootstrapping. Bootstrapping is a randomization method where you sample with replacement and just generate new samples over and over and over again. And every time you generate a sample, you calculate a mean. All right. Then what you end up getting is a collection of all of these randomized means, which 95% of them, or the middle 95% of that distribution, represents then our 95% confidence interval. What's interesting is that the standard deviation of that distribution is a bootstrapped standard error of our mean. All right, so there's some interesting properties. Now, how do we go about doing it? So we've gone ahead, we collected our data, and we have this sample. And then from that sample, we calculate a test statistic. For this, we're going to do a mean. But I've given in generic terms because it could apply to any test statistic. If we wanted to do confidence intervals of the median, we could. If we wanted to do a confidence interval of the variance, we could. Or of the standard deviation, we can do that. All right. If we wanted to do a sample and take differences between two different samples, we could do that. All right. So this applies to numerous types of data and numerous types of statistics. But what we have is we have our sample of size n, and we have our test statistic. We'll use the mean. Then what we're going to do, so that is our observed test statistic. Then what we're going to do is generate a new random sample. So we take that sample of size n, we're going to shuffle up the data, and then we will randomly draw with replacement a number equal to our sample size n. So if we had 1,000 data points, we will generate a new sample of 1,000 data points. Now we're sampling with replacement. So we draw out an individual, we record it, we put it back in, reshuffle, draw an individual, record it, put it back in, reshuffle. So you have the possibility of having some data points that are never sampled, some data points that are sampled once, some that are sampled twice, some that are sampled three or more times. All right, so that's sampling with replacement. That's going to be our random vector. And then from the random vector, we're going to calculate the same test statistic that we did from our original sample. All right, and this is going to be our randomized test statistic. And that is test statistic number 1, because we just did this one time. And then what we're going to do is repeat this over and over and over and over again until we have a large number of these randomized test statistics. All right, that vector, that collection of randomized test statistics will then allow us to calculate a mean and a standard deviation, all right, where that standard deviation then is the standard error of the mean of our sample. All right, we're not really going to be interested in the standard deviation or even the mean of that sample. If we did it correctly, then the mean of our randomized test statistic should approximate this observed test statistic. They should be pretty darn close to equal. Now, they're not going to be equal because of the randomization, right? It's random, but they're going to be pretty close. What we're interested in is the confidence interval. So what we do is we have this vector of randomized values. We're going to look at the 2.5 percentile and the 97.5 percentile. And those are going to represent our bottom and the top of a 95% bootstrapped confidence interval. Why is that 95? Because those two values mark out 95% of our values between those 2 points. All right, how are we going to do it? Well, we have to write the code. So let's go up to the board and kind of sketch out some generic code that allows us to do this. And I'm going to leave that up on the board, and we're going to do it each time. We're going to write out the code, and we're going to mark what each step is doing. Is that only controls there? Are there other light switches over there? Huh. Work order. So I'm gonna have to do. All right. So let's jot down. Let's get the code. And it's a shame to erase the sliders. 9 plus. Prove me wrong. All right. So we have our data. All right. We have our data, and then we're going to calculate our observed test. All right. So, what do we want to call it? Say. All right. Average observed ABE.obs. That'll be our average observed, and we're going to take the mean.
What does that say? We can't see it from back here.
Oh, ABE.obs. That's going to be, we're just going to call it a generic name. So this will be a mean of a vector, and what we'll do is dat dollar sign, something like that. Dat dollar sign vector, right? Whatever we have. So that's our observed test system. That's what we want the 95% confidence interval of. That's what we're looking for. All right, so what we're going to do is we have to set up some way to randomize our data, calculate a test statistic, and save it. So what I'm going to create is this RAV, randomized average. All right, and I'm just going to make a blank vector, C parentheses. All right, that's going to create a vector, but it's not going to have anything inside of it. It's an empty vector, or a null vector. That's this. This will create the vector to hold our randomized test statistic. I'm going to use TS for our random test statistic. And then I'm going to create a mean. Parentheses I in 1:1000, and then a curly brace at the start. So what this is telling R to do is that we're going to proceed and run everything that'll be inside of our braces. Run it, and every time we complete it, we're going to increment our count. So I is our counter. We're going to start at 1, and every time we get to the end, we're going to add 1 to it. And as long as our counter stays between 1 and 10,000, it's going to keep doing it. And then once it hits 10,000, it's going to do it, and then it's going to stop. Because at that point, the counter is going to exceed 10,000, and it'll be 10,001, and it says, I'm done. All right? So this will be our random, this will be our loop. Now what do we do in the loop? First, we're gonna resample our data. So we're gonna make an object called our data. This will be our randomized data. And then what we're gonna do is sample our data, or dat $back. We're going to sample that vector, dat $back, and we want replace equals t. All right, so if we didn't do replace equals t, all that we're doing is shuffling the data, and when we calculate the average, we get the exact same average as our randomized, or as our actual observed test statistic. Because it's the same data, all that we did was just change the order in which it appears. With this, when we sample with replacement, we're going to get a new vector. We're going to get repeated values. We're going to get some values that we don't get in our data, or we don't draw on our data. So we're going to generate a random data set, and then what we're going to do from this random data set, we are going to calculate our test statistic. And our test statistic is the mean. All right. So here's our mean of our bootstrapped, or our randomized vector. All right. Calculate the mean, and then we're going to save it in that RAVE vector, a randomized vector. Now I have brackets. Brackets. Who remembers what those mean? Anybody? It's called subscript. What is this referred to? This is our row. All right. So what it's going to say is it's going to take the vector, and at whatever row I is at the time, it'll put the mean of our vector. So the very first step, in the very first run through, I is equal to 1. As we said, for I in 1 to 10,000, starts at 1, generates our random vector, and then in the first row of this vector, we're going to save the mean of our data. And that's it. That's the end of our loop. So it goes through once, and then it jumps back to the beginning, increments our counter, makes it 2. All right, we're still good. So then we generate a new random sample, calculate a mean of that sample, and save it in row 2 of our AVE. And then it increments our counter. Now I is equal to 3. Generate a random sample, calculate the mean of that sample, save this in the third row. And it's going to keep going over and over and over again until we have 10,000 rows in this RAVE. All right? So this is our loop. So this is the loop. To get our bootstrapped vector. All right. So the first step of this is to generate a random vector. Create a random vector. Calculate the test statistic, the TS, and then save TS in the random TS vector. That's not a test statistic. We can phrase it. And then we repeat. So now we have RAVE. All right, at this point, we can take the average of RAVE, and that average should be pretty darn close to this. If we do a histogram of RAVE, what do you think the histogram will look like?
Normal curve.
Yeah, it'll look like a normal curve. And if we do a QQ plot, it's going to look like a normal curve because when we randomize our means, the collection of randomized means will approximate normality. So we can get that. Do we care what they look like? No, not at all. Because what we're interested in is the confidence interval. So what we're going to do is do our quantile function. All right. We want our quantile of this RABE vector. I hope that's right. I have a hard time remembering if this is quantile or quantiles. And if this is prob or probs, the yes at the end. So hopefully this works. If not, then we'll fix it. I think it is quantile, and then probs is plural. So this right here calculates the 95% bootstrapped confidence interval of the mean. And that's what we're looking for. All right, so if our $$ vec, that vector here, if that is normally distributed, or if that's normally distributed, then the 95% bootstrapped confidence interval, the BSCI, will be approximately equal to our parametric confidence interval. Where that parametric is our mean plus the QT function times this STERR function. So that was on our example. So it's one of these things where if we're normally distributed, our bootstrap confidence interval will approximate the confidence interval that we can calculate by hand using the QT function and the standard error. But if we're not normally distributed, then these things will not be equal. And I put approximately equal because, again, we're randomized. So everyone's going to get a slightly different interval. But they're going to be really close if we're normally distributed. If we're not normally distributed, then our confidence interval will reflect the underlying distribution. So if our data are skewed, we should see some skewness and asymmetry. All right. Questions? So, go back with this. Let's get R open. And let's get some of this code in here. And I might actually do it even more generically than what I presented. All right, so RStudio. So let's start with just getting a bootstrapped function together. And I'm not going to work with writing a function just yet, but we'll write the script. So bootstrapped confidence intervals. All right. General code. All right, so we're going to do general code. So for this general code, we're going to write it to minimize what has to be replaced. So that way you can copy this chunk, get it into a new document when you're calculating that one that needs to run this confidence interval. All right, And then we're going to try to minimize what has to be updated. So the very first thing that we're going to do is calculate or generate a new vector. All right. So the first thing we're going to have to replace is data $vector. So I'm going to create a new object just called vec. That's going to be our original vector that we're going to calculate our observed test statistic from and generate our bootstrapping. All right. So we're going to replace data $vector with your actual vector of data, of numeric data. So if it's just a vector that we've created, you don't need the data $vector. It's just the name of that vector that you created. If the variable is inside a data frame, well, you need your data $vector format. All right. Do we need to do the observed value? Not really, because you're going to calculate the mean anyways. What we're interested in is the confidence interval. So what we're going to do is create an observed R mean is what I'm going to call it, because this is for a general code for a 95% bootstrapped confidence interval. All right, so the R mean, that's going to be our randomized mean values. And then we're going to start our loop. I've got an even more generic one that allows you to specify sample size, or how many bootstrap replicates we want to do. So here's so for I in 1 to 10,000. And usually it's 10,000 replicates. We can go less, we can go more. If you are writing this for the very first time, I recommend just starting with 100, just to confirm that it runs, and then bump it up to 10,000. Because if you run 10,000, and it's a really long randomization method, if you're sitting there for 5 minutes, how do you know that it's still working versus it's in an endless loop and will never end? You don't. So if you do it like 100 times and it finishes in like 5 seconds, that tells you that if you bump it up to 10,000, it's going to take a little bit more than 5 seconds to run. But for us, we're going to do 10,000 because this is generic code. And then what we're going to do is create our rvec, which is our randomized vector. We're going to sample from the vec, and we're going to use replace equals t. So again, so far, the only thing that we've had to replace is that data $vector. Everything else is going to be generic. Once we have that rvec, now we need to calculate our mean. All right, and we're going to save it in row I of that randomized mean value. So our mean, we're going to calculate the mean of rvec. All right, and that's our loop. And then our last step is to do the quantile function. We're doing the quantile of r mean, where our probs is equal to 0.025 and 0.975. And that's it. All right. Now this is going to fail if I try to run it right now. And why? Why would it fail? Yeah, we don't have anything. We don't have data. We don't have anything in data, right? This is generic code. This is meant to copy and paste into another chunk, and we can run it. All right, so here's a demonstration. And this will be one that we did in the presentation. So our demonstration of how to use this, we have fish. All right, we've got 50 fish. We collected 50 fish. 10% were infected with a parasite. All right, so if we do 10 out of 50, that's 20%. Actually, no, let's do something else. We'll do this second. We'll do the fish second. So demonstration, let's create a new, let's import our data set. Let's use there it is. Which one should we use? Which one have we used? We did Roach, right? Roach data. Roach random data. Which one? Which one did we use? Roach data. Yeah, Roach data. That'll work. All right. So I'm going to keep it as Roach data. All right. I'm going to make sure I have strings as factors. Heading is yes. So I'm going to import it as Roach data. And let's look up where this came from, so we can reference it in our Markdown document. Let's see. I don't remember saying that. Oh, I don't think we used, I think we did Roach random data.
Yeah.
Let's do, okay, so we did Daphnia.text. Let's do Daphnia.text. So Daphnia.text was from 01B, the introduction to R. I think that can work. ASU, hold on, gotta go to here again. ASU, R, data. Yeah, that'll work. Daphnia.text. Daphnia. Yep, that'll work. Strings as factors. There we go. Growth rate. That's a good one. All right, so we will use Daphnia.text data from 01B intro to R lecture. All right, so that's on Blackboard. All right, we're interested in growth rates. We've got 72 observations, and let us, yeah, we'll just look at growth rates and demonstrate it. So, our goal here, calculate the mean and 95% bootstrapped confidence interval for growth rate. All right, so that's what we're going to use. And growth rate was a capital G. All right, so first up, we're going to calculate the mean. Daphnia $ growth rate. All right. And then we're going to have our bootstrapping. So when we report the data, we're going to report our mean, and then we have to report our measure of dispersion. And in this case, it'll be our bootstrap confidence interval. So what I'm going to do is going to go up here to this chunk, and I'm going to highlight it all, copy it, and paste it down here. And then, as I said, the only thing we have to change is that point. Data $vector to Daphnia $growth rate, because that is the vector that we want to calculate our confidence interval from. All right, everything else, leave it alone. We've written it in such a generic way to minimize what we have to change in this script. So then, I'm going to run it. And this is what I get. And you can see it ran pretty quickly, right? Super quick. 3.549, 870 is the lower, 4.147298. That's our bootstrapped confidence interval. So when we report it, reporting, the average growth rate was 3.852. I'm going to go to one more so I can see my growth rate was to the hundredths place. I'm going to go to one more digit for our mean. And then because we have one more digit for the mean, I'm going to go to even one more digit for the confidence interval. I'm going to move this down for you too. So the average growth rate was 3.852. And then in parentheses, I'm going to write 3.5499 to 4.1473. Now the question is, how do we report those values? How do we specify that these are the confidence intervals? So I'm going to just write 95% bootstrapped CI and then a colon. And that tells me then I know the mean, and then this range is my 95% bootstrap confidence interval. Note, you would have specified the number of iterations used to create the bootstrapping in your methods section. So at some point we have to tell the readers how many iterations do we do, because this is 10,000. This is 10,000 samples. And anytime we do a randomization test, we have to say how many randomization techniques we use, or how many iterations we use to generate our data. So this was 10,000. I had 3.599 to 4.1473. If I change this just to 10, I've got different values, 4.7 to 3.47. There's one that shifted up. That's narrower. All right, so the fewer iterations, we're going to increase the amount of variation that we have. But if I run 10,000 and run it repeatedly, my range, my confidence interval is going to be pretty good. It's really not going to change much. Yeah, we get some changes, but you know, 1/100th of a change isn't really that significant. Whereas with my sample size, or with my 10 iterations, I had some tenths, 2 tenths, 3 tenths difference in my bottom or my top. All right. So this was our bootstrap confidence interval. Yep.
And all kinds of errors.
Oh no, all kinds of errors. Maybe there's a mistake someplace. So it tells us it's in our back is not subsettable. Ready that. All right. That. So that didn't appear. So, question is, why doesn't that read?
Need to save it, redo it.
I don't think so. That should have run. It looks like it should run. Run. Option. Okay. So deck was created. It's I and 1, 2. Oh, hold on. Oh, there it is. You call that army.
Oh.
And then, I don't know. That was, no, we did. We have our, yeah, I did. I had our mean. That was right. Our mean difference is this. You forgot the our mean. And then quantile. All right. Other errors? Right. Just giving you the same thing over and over again. Drop down. Yeah. That is pretty good. I didn't use the front. Scan that back. That worked. And army. Bring my 4I.
Oh, yeah.
Let's change it. Let's change it. So, oh, hold on. Yeah, that's not data dollar sign vector. This is what we have to replace. So this was your generic, right? Okay, so we have it back here.
It's clear.
Looks like that.
Fire on it, I don't care. Treat it like a trailblazer.
3.5. No, it's changing. But why is it red though? I don't know. I don't know why it's red. Unless it's true. Yeah, or okay.
Well, it had gone off properly, and then also damped on the field, and just the shockwave of it, I don't know.
Yeah, it's working. I don't know why it's marked red on there. That's strange.
All right, so anyone else have errors. All right, so there's bootstrapping. That's of a mean. All right, but it's not. It's any test statistic. So this kind of demonstrates it. So we have 50 fish. 10 were infected with the parasite. So what we're going to have to do is kind of generate our own vector. So this is demonstration number 2. Number 2. All right, so we sampled 50 fish and 10 were infected. All right, so what I'm going to do is do fish, and we're going to create a vector. All right, so we're going to repeat 0 40 times, and then we're going to repeat 1 10 times. All right. So this creates a vector of zeros and ones, where 0 equals uninfected and 1 equals infected. All right, so the question is, why do this? The reason for converting binary data to 0 and 1 is that the mean of the vector will give the proportion of ones in the data set, or in the vector. All right? So just to kind of demonstrate, I made the fish. If I do the mean of the fish, I get 0.2, and that means 20% of our fish are infected. All right, so it works this way for any binary data. So instead of doing male and female, recode it to 0 and 1. And then when you take the mean of that vector, it's going to give you the proportion of whatever of those categories you keyed as 1. And this will then, if this is the proportion, or the probability of being infected, we can then do a bootstrap of this vector to get a 95% confidence interval of this single point, which is just a single data point proportion, without making any sort of assumptions about our underlying data. All right, so what I want you to do is try to do this, do your bootstrapping, get a confidence interval of this vector, and then we'll look at it on Monday. The other thing, what's that?
Study.
What? Study? That, yeah, we've got a week after that. Right, so it'll be the 1st. Is November 1st is a Monday. Yeah, we'll get our exam back so you can look at it and use it to kind of review. So the other thing, to be discussed. All right. What happens if we have missing data in our vector? And we'll talk about how we can kind of, our options. I think you probably have an idea of how you can adjust our generic code, our generic script. But we're going to talk about the pros and cons of our adjustments. All right. So we're going to be done. Just a quick review. We have our generic script. Save this. This is in my useful function script. So if I ever need to do a confidence interval, a bootstrap confidence interval, I copy and paste, and the only thing I have to change is that line. That's it. Now it's different if we want to do like a 99% or 90%. Yeah, then we have to change these, but for the most part, 10,000 is standard. All right. Lay this up. You needed it. And we'll pick this up on Monday.